Zoran and Nicola, thank you very much for the kind invitation. It's always a pleasure. So, I don't know what's going to happen because I had to transfer everything to a new computer. I could not downsize the files, so I'll decide as we fly along. Okay, so I'd like to talk a little bit about cooperative marine robotics, both from a theoretical and practical standpoint. I'm not going to get deep into equations, of course, but I want to stress the fact that in order to do good cooperative marine robots, you need a very good theoretical background on dynamical systems, navigation, controls, and things of this kind. So, of course, the name is very fitting, breaking the ocean surface, because we need to examine the ocean, and it's very complex because of the reasons I have there. And I always like to show these slides because that's what got me prompted to start working on cooperative robots. So if you want to communicate between an underwater vehicle and a surface boat, in this case, then you have the multipath effect. Everything becomes very complicated and it is extremely hard. And the data rate goes down considerably. However, if you transmit in the vertical, then you can avoid multipath and the data rate goes up. So see, this was essentially the idea behind the very first project where we tackled cooperative marine robotics or robots, and it was called Asimov in 2000. Marcus Cardew is here at the back of the room. He was with us at the time. So here, for the first time, we suggested that the catamaran and an underwater vehicle would cooperate, one being on top of the other one, and then they would be able to exchange data at a relatively fast rate, and therefore the AUV could go about its life, performing its functions and then uplinking data for the users on board the ship that could even transmit it back to shore. Of course, this was easily said than done. We didn't actually accomplish all of that. Because at the time, and I want to stress this was in 2000. Ultra-short baseline systems were big, bulky, and very expensive, and many other things were not there, okay? So things changed completely. So there have been some extraordinary game changers. The small processors, sophisticated sensor suites, new acoustic and even optical modems, and above all, from a theoretical standpoint, very good algorithms for cooperative motion planning, navigation and control, and so on and so forth. And I also would like to show this figure. I'm not advertising, but we have been working so closely together with Evologics for a long time, and this is what changed the game, at least for me and a couple of other people. Beautiful units that allow you to transmit information, to measure ranges between two spots, and estimate relative positions. So it's a mixed USBL range measuring device and the modem. So you have seen this from Evologics. So then around 2012, we got into a very interesting project called Morph. Many of us that are here cooperated in Morph. And in Morph, that's where I think we very seriously tackled the problem of cooperative motion control underwater. So there were many partners involved, and the objective of Morph was to map complex 3D environments, mostly on the cliffs, the vertical walls. And people have difficulty doing this because you cannot go there with a big ship and with an ROV and maneuver around because it's quite dangerous. So the idea was to develop a way or find a way of doing this automatically. And this we did with the Morph concept, whereby by Morph we mean a group of 1, 2, 3, 4, 5 vehicles. And each one of them specializes in its own thing. For example, you see here a vehicle that goes at the front and uses a side scan and a multi-beam and also forward-looking sonar to detect what's going on. Then there's a vehicle at the top that does navigation, simple in this case, using GPS, but communicates the positions to the underwater vehicles. These two vehicles are anchors, and because they have ultra-short baselines, ultimately they will be able to find out where they are. And then you can have a bunch of vehicles down there that I call the slaves. that sort of reach a certain configuration by just measuring ranges to the anchors, and then you'll be able to do a survey of the seabed. But more than this, when you encounter the wall, oops, something happened here. When you encounter the wall, there's these dens where they start transitioning, they position themselves against the wall, and they do some scanning, and one of them steps back to keeping communicating with the surface vehicle. So it's a dance underwater, where you actually need to communicate a lot in order to do both navigation and controls. All right, so to give you an idea of the kinds of things we did, I don't know if I'll be able to advance the video. So it was a huge group, the Morph group. So at this point, I don't think I can advance the video. So anyway, how can I? Sorry about that. Oh. I don't know, somewhere here. Yeah, this is not going to. Yeah. Okay. Okay, just wanted to show you. Oh, so the vehicle that goes in front knows what it is doing. The other one have to learn. The other ones have to learn on the fly. Here you go, everything going into the curve. And I wanted to show you this video. These are some shots from underwater where the vehicles are doing the formation control and actually talking to each other and doing the cooperation. And again, we were doing this by using the modems and the ranging device in the ultrashot baseline of Robotics. So then at the end of the day, we go home. Okay. Obviously, I'm not good at operating this one. So it's, and then, okay, fine. All right. So in order to do this, we need these wonderful seagoing machines. These are the ones that we use back home. They are called the Medusa. And of course, in the Morph project, we were playing with other vehicles from other partners. So here you see the kind of a vehicle that we use that has two segments, because right from the beginning, we knew we would be dealing with cooperation between or among surface and underwater vehicles. So each vehicle is capable of working at the surface or diving. But when it is at the surface, it should be able to get GPS, use Wi-Fi, and at the same time to have a body under the water to be able to communicate with the other vehicles. And we ended up with this kind of format. Okay, so then the next project came up. It's probably the most exciting one I've ever been involved in. Geophysical surveying or seismic surveying or geotechnical surveying. They are not similar, but anyway. So when you want to find out what is underneath the seabed, so classically you have a ship with an acoustic source, a sparker, a boomer. It generates a wave that propagates, insonifies the water column, hits the bottom, penetrates, comes back, and then the sound reaches the hydrophones that are pulled by the vessel. These are called the streamers. So this is how it is classically done. So you see here one of these vessels with the streamers. Now, it's a very costly operation. The boat is very expensive. The streamers can get entangled. And then there are some strange effects called feathering and things of that kind. But anyway, the problem is that when you want to do what we call 3D seismic surveys, the price per kilometer square is outrageous. But the kinds of things you get are amazing. This is what you get. Well, it doesn't make much sense to me because I can't read this. But our friends from the north, from the city of Aveiro, they are geophysicists, and they can actually process the data and show you slices. Oh, is it this one? No. So can't I simply play the video just by clicking here? No. But I cannot control it. So these are slices. After the processing, this is what what is underneath the seabed. And I find this fascinating. I mean, it's very high precision. I mean, they are diving virtually to about 150 meters here. And you see all the details with the acoustic sound. So what was the mast concept? Essentially, we wanted to get rid of the ships because they are extremely expensive and cumbersome. And also because you have to maneuver the ship and the streamers at the same time. They are coupled. So there's no flexibility. So the idea was to replace, I'll show you here, to replace the ship by 1 or 2 autonomous surface craft equipped with sparkers. And then instead of having the ship pulling the streamers, the idea was to have a bunch of AUVs that could either operate at the surface or dive and pull the streamers. Now you have an antenna that you can configure geometrically, and in fact you can lower this antenna and thereby increasing the resolution. So this was the beginning of the WeMust project. So, but if you can't, sorry, because I really would like to go to, so sorry, I wasn't making it. So it's control.
Sorry, what do you want?
To switch to that mode that you showed me? Yeah. No, but I escape. Okay.
So just play the video. And
241. Yeah, I know. Yeah.
And then skip to 241.
It's not playing. So I think I'll sorry about that. 241. Okay, so here, and then I'll press escape
makes
again,
it possible to change the shape of the acoustic antenna. This is very important.
Okay.
Because in this way,
okay, so that's an artist's rendition of what's going on with the vehicles pulling the
is
streamers,
potentially higher.
so on.
Furthermore, the lack of physical ties between the surface vessel and the acquisition equipment.
Yeah, this is going to be hard. Anyway. Okay, so there's a new concept of automated seismic surveys. And here for the first time we had to operate vehicles, like including our Medusas with the streamers. And you see here some of the operations. I should be able to show you. Well, I'm not going to spend too much time with this because it's going to take some time. So just to give you an idea, so these are the Medusas, and of course the Italians did the same with the Falagas, deploying the streamers, and then we run some tests of the vehicles flying along and doing coordinated motion controls. So the streamers are supplied by this company, GL Marines, in the Netherlands. And here we were executing what I call a cooperative path following maneuver, but it's taking too long, so I'm going to skip it. Now, in order to prepare the sparkers so that we could replace the boats, this was quite scary because we have our vehicle, it's called the Delphin, that was not prepared to carry a sparker. But here is how you install the sparker down there. So there's a bunch of electrodes on both sides. And then you inject the power, I think it's about 4.2 kilowatt. And there are the sparks, the water evaporates, and then when it collapses back, it generates the sound. So from a safety point of view, it was quite a challenge. But here is the vehicle with the sparker. And of course, the Italian team did the same with another sparker. This gives you an idea of the very first test where we had the 2 vehicles that were actually carrying sparkers. And then there are 1, 2, 3, 4, 5 vehicles tagging along, 4 underwater. So again, there's a big orchestra going on here because you have 3 vehicles at the surface, 4 vehicles underwater. You have to find out exactly where the vehicles are, where the streamers are for georeferencing purposes. So again, navigation and control were extremely important. So what's the theory behind? Just a glimpse. It's very important to work on cooperative network motion planning, navigation, and controls. And that's how we see it. So first you start by doing motion planning, like when you first have the vehicles up there and they are all scattered, and you want them to start a mission You want them to travel to initial site, all aligned at the same speed, and then start the diving maneuver. That's what I call the cooperative motion planning, and then the mission starts. Then cooperative navigation, where they help each other finding out where they are, and given that we know where we wish them to be and where they are, then we have the cooperative motion controls. And here we have a big problem, because if they are underwater, they have to communicate via the acoustic channel with the low bandwidth. Luckily, we were responsible for this task, and we sort of had learned a little bit about this when we applied these to air vehicles. And that's some work that we did back with the guys in the US, Naval Postgraduate School at Monterey, and also people at the University of Illinois. So the key concepts are exactly the same. So from the point of view of a general architecture to make these things work, what do we need? Cooperative navigation, control, and planning. So let's look at the formation. You have two sparkers on two vehicles at the top. That's what you have there, the sparkers. You have two vehicles that are going to work as anchors. They know where they are at all times. And now you have the four vehicles underwater pulling the streamers. Now, the vehicles that are at the surface know where they are using GPS. The vehicles that are underwater are going to find out their position by measuring range to the anchors, and then the anchors transmit their GPS information down. And in all this, again, we were using the units of EVA logics. So the basic building blocks that you have, two acoustic sources on the catamarans, then another catamaran on the side, two anchors, and the four vehicles underwater. I'm not going to go through the explanation of how this thing works. Just to let you know that, again, it's a big symphony, because we have acoustic communications and ranges. So you have one vehicle range measurements, transmitting information to the underwater vehicles, the same from this one, the same from this one, and then we have Wi-Fi to make the vehicles at the top coordinate. So how do we find the position of the vehicles underwater? So each one of the catamaran emits a signal. So you have catamaran number 1, catamaran number 2, and then these signals reach these streamers here, and the streamers will find the range, will find their positions with respect to the baseline, and then one of the catamarans will transmit to the vehicles the real position of the guys on the top, so that you will know where they are, and then they track a trajectory that is imposed by one of the vehicles, and that is being transmitted in real time down there. Okay, so again, I'm not going to go into the details. We found this solution to be very scalable. There's something that is very uncomfortable, because we are not really communicating from underwater vehicle to underwater vehicle. We are all going through the surface, so that goes against my principles, because I want to use cooperative motion control tools. I would like for each vehicle to talk to a few neighbors, but we don't have the state-of-the-art on acoustic modems and how fast you can communicate. It's not there yet. So there's a lot of work to be done on that front. So cooperative motion control, there are many practical constraints. We have a heterogeneous vehicle fleet, and above all, there are no fast communication among the members of the fleet. So this is the architecture that we had for the WeMust project. So there's the vehicle fleet. There's the cooperation among them. They have to enter a dialogue with each other to decide, now I go ahead, now you step back, so that we reach a certain geometrical formation. And then ultimately, each vehicle has the inner loops running by controlling the speed, the heading, and the depth. And then they talk to each other, then keep doing this. So when it comes to the single vehicle primitives, the guys from ISME in Italy were in charge of this. So there are inner loop controllers for search speed, heading, and depth references for each vehicle. Hold position when we are waiting for the mission to start, and go to point with specific coordinations, what I call waypoint, when we want to maneuver them to a certain place, and then we engage the cooperative motion planning. Now, when it comes to multiple vehicle primitives, it's very interesting, because you start with path following. So each vehicle should have the capability of running a primitive that is called path following. You follow a certain path with a certain speed profile. And then you bring everything together and you have cooperative path following or trajectory tracking. So, as you know, in trajectory tracking, you want to be at a specific spot at a certain time. Path following, it doesn't matter. You just go over a path with a speed profile, but it doesn't matter if you are at that spot now or 5 minutes from now. Okay? So when it comes to path following, all the algorithms that we use were extremely simple. So essentially, you can use line of sight, you can use more sophisticated methods, but essentially, if you have your path that you have to follow, we have it here, you have a path that you wish to follow. For example, you compute the closest distance to the point, you look a little bit ahead, you point the nose of your vehicle, and you keep doing this. The paths are parameterized in a specialized manner. It could be the length or something else. Now you bring the vehicles to do cooperative path following. How do you do this? And you see the vehicles, they are doing path following. Each one of them is executing path following, talking to each other. And for example, if you want them to go shoulder to shoulder aligned, they have to do the synchronization not on the length, but on a special parameter that is dependent on the length that we call gamma, and you declare victory when the parameters gamma are all equal. So cooperative path following, you can achieve also certain formations. They don't have to be just side by side. And then trajectory tracking is different because then you want to be at a specific point at a specific time. And then you have coordinated trajectory tracking, which is what we use for WeMust, where the top vehicle executes the trajectory and then downloads the trajectory in real time to the other ones, and they are supposed to track. So here is an idea of how we do this. So the top vehicle accumulates data from GPS, generates a buffer, thus a path generator, a predictor, sends down, and then the vehicle down receives it, knows where it is because it is using the anchors, does tracking controller, and then goes to the inner loops, and hopefully everything will go okay. Now, it's very interesting because I'm not familiar with these kind of details, but if you ask me, what formation should we run? So from talking with a geophysicist, it's very interesting because I'll show you a video here. So this is a simulation of a sparker and then two vehicles with streamers. And the bottom of the ocean is divided into cells. What is important is to illuminate with sound each cell from as many angles as possible because then the accuracy goes up. And this will be very important for something I will tell you later. So this is an excellent cooperative motion planning problem that we have not resolved, which is it's not the usual stuff, make the vehicles go from here to there and minimize the time or energy. No. Increase the information available to get a good map of the seabed. How this can be embodied in some type of cost function, it's not clear, but I think it's a very exciting problem. So this gives you an idea. All right. So again, you have the two catamarans, and they are running the sparkers. I'm afraid you have to wait a little bit, but I really wanted to show you. This is seen from the top using a quadrotor. We were doing some tests with a catamaran together with the people from UNIZG-FER in Italy. And here you'll be able to see the power of the streamer. These are the sparking. Boom, 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 boom. So it's boring. After 1 day to have two sparkers going forever. Ton. Anyway, so that's the team. Okay, well, what I'm showing you is the comparison between real and the simulated cooperative motion planning. So this was the responsibility of the people at Hertfordshire. So we had a bunch of vehicles. You wanted them to go to specific spots and start the missions. And then here we are comparing whatever we did before in MATLAB. And this is real. I mean, we have the two sparkers, one of them going a bit crazy over there. but it will converge, and then the other vehicles getting into the formation. So that's an example of cooperative motion planning. Now, this I would like very much to show at 1:33. Okay, oh, I did it. 1:33.
And it consisted of
These were the final tests in Sesimbra, in Sines, Portugal. Sines was the birthplace of Vasco da Gama, so it's very fitting. So, 2 sparkers, and then another extra surface vehicle, 4 vehicles underwater, and then we did the survey. So I hope it will come up soon and fast.
Of performing roughly 7 laps
it's
of a
not
path,
running.
Scanning an area of approximately 100 meters
Sorry
by
about
200
that.
meters.
For some reason, it
The
stopped.
acquisition was very successful, for it proved that the design system
Yeah, I
can be
really wanted
employed
to
to
show
collect
you
seismic data autonomously.
or something. Okay. Okay, so let's get back to that, no problem. But now it's stuck, right? Okay. Sorry about that. Oh dear. Not responding. My Mac wouldn't do this. Yeah, back to the intro, please. Okay, I have to be more pragmatic here regarding the videos. Sorry about this. No, don't worry. Okay, something that is going to be very important for the rest of the talk is that here the geometry of all these things was essentially fixed. 2 sparkers, and they decide what they do. And then the vehicles underwater learning on the fly what they are doing and tracking. So I told you that it's important to hit each cell from different angles. It's very hard to do this using this geometry. So the geophysicists told us that the ideal thing would be for the sparkers to circle around the center of mass of the vehicles underwater. Yeah, that would be easy. So I'm going to skip that video. Yeah, that's here. Yeah. So that's some of the. It's too bad we can't see the mission, but that's fine. That's some of the data that we got. So keep this in mind. It would be lovely to have the sparkers go around. And those of you that like cooperative motion control probably think immediately of what people call circular pursuit, circular target pursuit. An interesting development is that at the end of the project, the industrial partners told us, look, this is all very lovely and we had a lot of fun, but I don't think this is not ready for the market yet. However, there is something interesting that you could do, because there is a market for geotechnical surveys in shallow water, for example, in harbors or near shore. So can you deliver a compact system with 1 sparker and a bunch of streamers to do the survey? So we changed the Delphin. So what you see there are the arms, and the Delphin is pulling 4 streamers, and now you have a compact unit, because you excite with the sound, you acquire data. I'm sorry, at this point, I'm not allowed to disclose the data that we got, but it was simply mind-boggling, because we were doing this near shore and using the same type of slices that I showed you before. We could actually penetrate, and when we reached 60 meters, yes, well, this was the old shoreline about 3 million years ago. It's really exciting to be able to use these kind of tools. So that's the we must. In we must, we use essentially acoustics. What about using optics? Why can't we use optics? Well, because of the range, of course, right? But I personally convinced that when we want to cooperative motion control and the vehicles are very closely packed, like say 5-6 meters from each other, why not use optical modems? And it's very interesting because we developed this cute Blu-ray acoustic modem. Oh. Yeah, the problem is this is going to take a long time, and I don't... Okay, so believe me, we have the vehicles underwater, and we could reach synchronization by exchanging data over the optical modem, which was very exciting. The problem is that the modems are very, very directional, and we have to deal with this, so I don't have the time to do this. Now, what are the next steps? So new techniques have come into the market, mostly using ocean bottom surveying units, OBSs, where instead of having only the streamers in the water column, you actually have sensors at the bottom. Then they will be able to sense both the S and P waves and decrease the resolution of the survey. So this is a proposal that we submitted. It was not approved, whereby we have the sparkers, and then we would start by deploying in a controlled manner the OBSs, and then have things with streamers and magnetometers and do a combination. So I think the future in what regards geotechnical surveying is along these lines, where you have multiple vehicles, different types of sensors, and then you have to guarantee that you do the coordination of all this. So before I jump to something else, let me tell you about the project that we just submitted together with the University of Porto and MIT. And I think this will be very exciting in what concerns multiple vehicles. So it's SOS for Atlantic. It's a new Portugal MIT initiative. And the idea is to focus on surveying ocean fronts. And João Sousa gave a presentation on this. So we won't be able to merge satellite data, aerial data, and data acquired with marine robots. So you start with the big vision, then you run some models, you predict where the fronts are going to occur, and then you deploy our assets in an optimal manner to further refine the data and therefore the models. So hopefully it will be approved. There's modeling and forecasting, multiple vehicles, that's why I'm mentioning this, and then the ecosystem studies. And what is exciting is that we are bringing lots of assets into this picture, okay? So a showcase of technological assets. Now, I want to give you a technical detour, but I'm going to do something complicated, which is to exit and go to the other one. And then I'll probably go back to this one if I have time. Because I wanted to give you, yeah, the other presentation, please. Yeah. Okay. So, cooperative motion planning, navigation and control, lots of exciting problems to solve there. Now, let's think of an exciting problem. We must. I think it was a compelling example of the use of multiple marine robots. But I told you about the problem. Maybe there's not enough excitation of the cells down there. So I'm sorry I could not come up with an elegant way of doing this. This is the way I'm showing the streamer or the spark vehicle doing these maneuvers. This is what you really would love to have. I mean, to have the streamers down there, to have the two sparkers up there, finding out where the center of mass is, and then executing a motion along a circumference. But this cannot be programmed offline. They have to react to each other. For example, if the 2 or 3 vehicles on the top are falling away from formation because one of them is weaker, then the streamers should wait and come back on speed. Or for example, if the streamers are slowing down for some reason, these guys should slow down too. So this is the perfect combination of everything: planning, navigation, control, communications, networking. And I find it fascinating. So I decided to prepare a few slides. I hope they will not bore you. To introduce what is called cooperative moving path following. So the pioneering work on this was done by people at University of Porto, together with a gentleman from the Air Force, where they introduced this concept of moving path following. So in its simplest manner, you have a target that executes a trajectory, and you'd like for a bunch of vehicles to circle around and move in cooperation. That's the simplest thing. So, of course, these papers by Tiago, Encarnação, and Aguiar are extremely well done. But I sort of figured out, can we simplify this and make this much simpler? We haven't not done this in practice. That's what I'm sharing with you because I think it's a nice theoretical problem. So, basic problem. How do you make a single vehicle go to a certain path that is moving? And I was talking with a gentleman from the MIT, and he was mentioning landing of a spacecraft on a tumbling asteroid, and it clicked. I mean, immediately you see what you need to do. So what you need to do, you match up the linear and the rotational speed of the two. So you learn about the trajectory of the asteroid, both the position of the center of mass, the rotation, and now you are in sync, that's your feed forward kind of thing, so that the spacecraft stays on top of a landing patch. So the relative drift and position is now 0. So you are essentially seeing something that is static. Now you look at the landing site and do the final corrections. But now you only have to control with respect to this local reference frame, and that's exactly what you need. So there's the center, so there's a reference frame with a path. I'm going to go for the simple case where the path is not rotating. So the center evolves with a certain speed. There's the center. There's a non-rotating frame. The path is attached to the frame, and the origin undergoes an arbitrary motion. How do we make a vehicle converge to this path, the center of which is going along a certain curve? Well, remember the asteroid. Go deep inside the reference frame attached to the path and forget everything else. And pretend that you are stationary in that reference frame, and now you start moving on that reference frame to drive to the path. So focus on the frame P and solve the path following problem in P. So if you have a certain point mass body, I'm doing this for a simple case of kinematics, and then you decide at what speed you should go based on where you are and where the path is. And this is what we call a guidance scheme. You can use line of sight or something more sophisticated. So in the end, you can come up with a law that tells you what velocity to reach so that eventually it will go in the direction of the path. That's it. So how does the guidance law look like in the inertial reference frame? Well, it's simple because the position is equal to the position of the center plus this thing that you are controlling. But because the path is not rotating, you have the identity, and therefore everything becomes very easy. So first, you estimate the position of the mass point in the inertial reference frame. You convert to the local reference frame. You run your path following system using a kinematic guidance law there, and then you go back to the inertial reference frame, and that's it. As simple as that. So here is the system where you have all the data that you require, the things that you have to compute, and then you keep doing this. Okay? Things get a little bit more complicated. Now you have a rotating path. So now you have the path here, but it could start rotating. So what's the big difference? The big difference is now that, okay, how do we make the vehicle converge to the path? There you go. It's still the same equation, but now the rotating frame is rotating. Okay? So when you do exactly the same type of computations, where you write the position of this gentleman is equal to this one plus that one, and then when you compute the derivative in the so you solve the problem in the local frame, you go to inertial, and when you compute the derivative, you have a bunch of terms. You know how to do this. Derivative of the rotation matrix. It involves the angular speed and stuff. What is interesting is you get the guidance law in P. It's trivial to get. And then you go back to the guidance law in I by adding the linear velocity of the center, by including a term that has to do with the angular velocity of P, and then the guidance law this should be in P. So it's essentially the same thing. Okay, so now let's get it more complicated. Because not only, well, okay, all right, I'll skip the other part. Now, instead of having just one tracking, how can you make more than one track? It's not more complicated. How do you make multiple vehicles converge to a moving path? All right, having multiple vehicles converge to different paths or to the same path, that problem has been solved. And you can even do that by not communicating too much. So essentially what you have to do, two things. You make each vehicle converge to the path as you did before, and then they also talk to each other to decide whether to speed up or slow down. So the local velocity vector for each vehicle now has two components. One has to do with pure path following, the other one with coordination, and that's it, you are done. So now when you have three vehicles and you want them to converge to the path and reach a formation, the three local velocity vectors are going to be generated by, so I'm not showing the details, running the coordination and the path following, and you are essentially done. And then you convert the local velocity vectors for the guidance law to inertial, and you feed this to the local autopilots of the vehicles. That's it. And now one step further, because I didn't want to go through all the details, because you don't want all of this to be programmed offline. So now what do? The target executes a path following algorithm. The pursuers perform CPF with respect to the moving path. But now you have to combine these two. They should talk to each other. The center of the moving path executes path following with a speed that depends on the performance of the pursuers. If one of them starts lagging behind, well, I'll do it more slowly. But then the other one will have to react. So you see, that's why I wanted to talk about this problem, because I find it so fascinating. Because it has everything. It has cooperative navigation, path following, cooperative path following, and all these things there. So overall motion is very compliant. So the pursuers and the target cooperate. This is in striking contrast with what we have in target tracking. And of course, this is easily extendable to multiple targets information. So I think we have the key ingredients to do what we set out to achieve from a theoretical standpoint, and then we'll try to do it in practice, which is to have a bunch of streamers moving, a bunch of pursuers up there, they talk to each other, and this will be all very compliant. So to show you a little bit of how this works, this is the simple case where you have three pursuers and you have a target. And then at some point, it's not clearly visible here, but there's a mechanism that detects if one of the pursuers is not performing well, then it's raising a red flag. I don't think you can see very well. So they actually slow down, and when the pursuer comes back to the path, then the speed picks up again. It's very interesting that in the simulation that you are seeing here, the vehicles are not communicating at all times. We are doing what we call event-driven communications. So, in a nutshell, each vehicle is talking to its neighbors. You have to define what the neighbors are. And each vehicle is running, I am a vehicle, I run a model of what I think you think I am doing. And when there is a discrepancy, I broadcast. And by doing this, you save a lot on the amount of communications. So it's fascinating. And then, of course, you can use this if you can imagine, I'm about to finish. If you can imagine that the target now, instead of being just one vehicle, it's a bunch of streamers, then you see what we have, a lawn mowing maneuver that is perfect for geotechnical surveying, and you have the sparkers floating around illuminating the scene. So in order to get ready, I'll have the same problem with the video. In order to get ready to implement this, we have implemented all this stuff in ROS in a distributed manner, running on different computers, the different vehicles, and then we sort of visualized what's going on using the Unity software. Oh, this is very slow. Is there a way you can help me? It's the very last video. Sorry about that. So it's, oh, it's escape, right? Escape. Oh, let's go to that. Right. Yeah, there you go. That part I know. Okay. So you see one of the vehicles is going along a curve, and the other ones are doing the circular path following. And I personally find this very interesting because we are running the different algorithms on different computers. Here we are running a simulation of the acoustic modems using the software of Evologics. I think it was via the web. So it's a very realistic scenario. Okay, I'm sorry. I had a bunch of other things to talk about, mostly about cooperative motion control using event-driven communications and MPC schemes. I simply don't have the time, so I have to stop at this point. Thank you.
Very much fascinating
Okay. Yeah.
talk.